Okay, so our next part of this unit is strictly non-calculator, okay? So what we're doing with you guys is we're developing how to factor these pieces out, how to work these problems without a calculator. So if you're copying notes right now, I want you to actually stop and follow with me, because we're going to copy these out together as we go through, okay? But I really want you to be able to see what I'm doing and ask those questions that I'm asking you to reflect on if you're not understanding as we go. All right, two big pieces of imaginary numbers, okay, are the fact that I squared is equal to this negative 1, and I by itself is equal to the square root of negative 1. Now, what I'm going to first show you is where do these come from, and then how and why are they used. Because imaginary numbers, some of us know what to do, but we don't even know what they represent. We don't know why do we do that, okay? So let's first start off with what we're looking at. I is equal to the square root of negative 1. And if I asked you guys, I want you to develop, how would I get I squared? Algebraically, what am I doing to get I squared?
Multiplying it 2 times.
Yeah, I'm multiplying it by itself 2 times, or I'm squaring it. Okay? So if I square the left side and I square the right side, I will end up getting I squared is equal to negative 1. Okay? Because if you square a square root, you answer this for me, please. They cancel to what number? A square root that is squared, what number does that cancel to? 1. You're right, the number that's inside, but it's an understood form of 1, right? It all cancels to an understood form of 1. And 1 times this negative 1 gave me a negative 1 answer. All right, now, let's look at your Algebra 2 skills in regards to developing what I cubed and I to the 4th equal. Guys, if I wanted to ask what I cubed was, all it represents is a product between I and I squared. Because what do I do when I multiply things with the same base? What do I do with their powers? I add. So this gives me I cubed. And I squared, we know, is a negative 1. We know that I is the square root of negative 1. So what would this equal right here for I cubed? What would I get? What's this negative 1 right here multiplied with the square root of negative 1 going to give me as a final answer? And don't be afraid, just say it out loud. Not a positive one, only because this negative is on the outside. So it's going to be a negative, it's all good, square root of negative 1. You with me? The negative is on the outside. Now, let's develop how would you get I to the 4th. I to the 4th is I squared times I squared. What's I squared anyway? Negative 1. Another I squared is negative 1. And if we are multiplying, because that's what we're doing here in between, then we would get a positive 1. Okay? So, this happens in a pattern, guys. So if I asked you, what is I raised to the 6th? Okay? The way you could do this is you could see the pattern of 4. You could break it up as I to the 4th times I squared. We know that I to the 4th is 1. And we know that I squared, which is over here, whoops. I squared is here as a negative 1, will give us a negative 1. So that I know the product would equal, I6 would be negative 1. Now there's a faster way to do this, okay? If it happens every 4, all I have to do is concentrate on this number and see what is the remainder if I were to divide by 4. Now we've been doing long division with polynomials. We can do it with easier numbers back like this as well. We know this would be 1. When we subtract, we have a remainder of 2. This remainder of 2 means this, guys. If you want something that'll have an answer of square root of -1, it's if its remainder is 1. If the remainder is 2, it will be -1. You with me? Now, how about this? For a square or a negative square root of -1, what would the remainder be? 3. Be careful. What would the remainder be for this one? 0. Nice. The remainder would be 0. Because if you could have a remainder of 4, why don't you just divide by 4 again? Okay? So remember, our remainders are always less than that divisor. Otherwise, we didn't divide enough. Okay? Now, so real quick, if I use this, and I say, because you could see this on ACT or SAT exams, if I have I to the 713th, I was like, what does that equal? Okay? All I would do is divide it by 4, so 713 divided by 4. I'd get 1 subtracting with 3, okay? Then I would get 7 for 28, which is a remainder of 3. Bringing down this 3, it'd get 8, which is 32, which is lastly a remainder of 1. If the remainder is 1, what is my final answer anybody? Square root of -1, because here is where that category would lie. So you'd say the square root of -1 is what I to the 713th power equals. Okay? Now, where do they come from and how are they going to be used? Watch. Okay, so if I told you you have zeros at 0, 1, and 11, and I told you guys write that for me in factored form, what would you write over here in parentheses? You could put x plus 0 or just x, and then what would you put for this? X minus 1, good, and then this one? X minus 11. So I have this right here written in factored form of a polynomial third degree. Now, it is a little review. This means that those x-intercepts would go at 0, they would go at positive 1, and they would go at a positive 11. Can someone tell me, is it going up or down as I go to the right? Up. And the reason of that is because these x's multiplied together are what? 3, yeah, you're right. You're 3, x to the third power, you're right. But I'm saying, what makes it go up as I go to the right? They're positive, right? So it'll go up to the right. Because it's 3, what does it do as it goes to the left? Down. And it has this kind of x cubed feel to it. There are 3 x-intercepts, or a possible 3 x-intercepts. How many change of direction? Up to 2, okay? And then it will look something like this. Okay, watch. You have 3 x-intercepts. Sometimes you may have a graph that looks like the following. It'll go through, but then it wants to come back, but never actually goes through the x-axis and goes back up. You have 2 changes of direction. That means it could be x cubed. But there's only one actual real x-intercept. You with me? These they're possible as far as being right here, they don't ever cross the x-axis. That's where the imaginary part comes in. We are going to learn how to account for those this unit, or this time, the second half. But this is like, theoretically, if they were able to come down, yeah, we would have 2. Because then the whole total would show that there are 3 roots. But now we're going to work with imaginary numbers where they still exist, but we don't write them as x-intercepts. We're going to be using i's, square roots of negative ones, and all those. Okay? That's where we're going with this. All right. So let's go back to our notes. So I wanted to address something real quick because there is a slight error here. I to the 8th could be written as this. We know I squared is -1. So -1 to the 4th is +1. You with me? You can do it this way if you want, or you can do that 4's trick that I showed you of taking this 8 divided by 4. What's your remainder? 0. So what is it? It's whatever I4th was equal to, which was a +1. And that was from that chart that I just showed you. I all the way to I to the 4th. Okay? Now, help me find the mistake on this one. Okay, it was an honest mistake, but where's the mistake that you see here? Is this correct so far, yes or no? Yeah, that's correct. What does I squared equal? -1. What's -1 cubed? -1. Don't be afraid, guys. -1. But what's -1 times I? -I, isn't it? And what did we say I was? Because remember, I and I squared are the ones that you're memorizing. Those are the big ones. And in my opinion, I think I squared is more important to memorize. But what is I all by itself? The square root of -1. So this right here is going to come out here as a negative. So this should actually be the negative square root of -1. You can change that in your notes, please. That's the only thing that you will catch. That's a mistake on this first sheet. Now, what I'm about to show you, some of you, depending on where your strengths are with Algebra 2, simplification, will need this for review. I'm going to show you how to simplify radicals. Okay, here we go. Some of us are strong with this. Some of us need some help. Here we go. If I asked you to square root 100, what's the answer? Okay, so 10, but then I heard plus or minus 10. Okay, here we go. The plus and minus 10 happens when this expression is set equal to a variable. Okay? So if you have something that looks like this, look, and I'm glad that you said plus or minus because that's where we're going. If you had something that looked like this, and I asked you to solve for x, you would square root both sides. This would be x, and here, just like Saeed said, would have the plus or minus 10. He's absolutely right if I have it equal to a variable squared. You with me? Now, if I just have the number here, yes, it's plus or minus the 10, but what I really want you to just concentrate on for now, and you're going to see the different variations, is just a 10 for now. Okay? Alright, so there's that fundamental. Now, what if I had this next one that had square root of 125? Not so easy. Okay? Some of us can see it. I can see it in your faces and I can hear it. Those of you who already know this, here's what I'm going to say. There's two approaches. There's one that is long, but you will get the answer if you methodically go through it, and then there's a shortcut. Let me show you the long way first. It's prime factorizations. So you're trying to divide this by prime numbers. Okay? Here we go. In case you forgot. A prime number is a number times 1 where these are the only factors, okay? And these are not equal to each other. So what's the first prime number in existence? 1. Not 1, because they have to be different. These have to be different from one another. 2. So 2. So let's do 2. And check this out. 2 times 1, those are the only factors that would create 2. You can't do anything else with integers that you multiply them together to get this 2. And the fact that they're different says 2 is prime. What's the next prime number? 3. Let's keep going. I want to go to a certain spot and I'll show you what we're going to do with this. 5, 7, not 9, because 9 is 1 and 9, and then 3 and 3. 11. 13. Okay, so that's good enough. All these are numbers that are prime. So if I looked at 125, I can break this up by dividing by, can't do it by 2, but I can do by not 3, but 5. Okay, so if I divide 125 by 5, it's the same as 5 times what? 25. See what I'm doing? And now, watch, keep going. I can break this up by 5 times 5, and still this right here is the remaining piece. And now this is called prime factorization. I broke everything down to its bare bones prime numbers. Now, some of you saw it here, and you're like, just take it out as a 5, and you're absolutely right. Or some of you don't see it until here, where you take out the pair as 1. And this last 5 that is all by itself stays in, because they only come out in couples, if you will. They only come out in a pair. You with me? Okay. So this is called simplifying this radical. Okay. This is prime factorization. Guys, sometimes it takes forever to do this. The way I want you to do these kind of simplifying, which you have to get good at, especially for this unit, is the following. I will look at 125, and I'm going to try to divide it by a number. Now, listen to the numbers that I'm saying. The first one that I would try to divide it by is 4. The next number that I would try to divide it by would be 9. The next number that I would try to divide it by would be 16. These are the squares. These are the squares. Like I said 4, I said 9, I said 16 if there was 4 squared. 5 squared would be 25. You see what I'm saying? So I would try to divide this by 25 and immediately get to this that I know I can factor this out, or sorry, square root this out as a 5. And this one that didn't make it as a couple stays in all by itself. It's a lot less work, I guarantee you, if you have that approach. But you have to know what you're dividing it by. Okay? Alright. Now let's work on simplifying these radicals with imaginary roots. Here we go. I have a square root of negative 81. Alright? So I'm going to do it off to the side. And you can watch me go through this. I'll do it like this. Alright, so we have square root of negative 81. And I know this is already written in your notes, but some of the ways that I group this stuff can actually make a little clearer sense. Now, the square root of negative 1 times, and this is for bonus points if you get it, and you're able to explain this. The square root of negative 81 is the same as the square root of this times the square root of 81. True or false? True. Okay. What does the square root of negative 1 become? I. What does the square root of 81 become? 9. Could I write I times 9 as 9i? Yes. Yeah. Okay. Now look. With that being said, would it be a plus or minus I? Not yet, because it's not equal to a variable squared yet. Okay? Now, wait, is I not a variable? I is not, so I is a, that's a really good question. I is like a variable, but all you're doing is with I, is you're treating it like ends on series and sequences. Okay. It can be a variable, but not the way X and Y are, okay? Okay. Alright, here we go. let's look at, okay, so you knew this rule is the same as this. Okay, guys, I didn't even discover this until recently, and I'm not even joking. With a math degree. Look, you're absolutely right. Where did you learn this? What class did you learn these properties in? Last year in Algebra 2. Yeah, you're absolutely right. Now look, what if I had this and this? Is this the same as this? I mean, you would think so. If I can bring these from two different square roots to be able to multiply together, then I should be able to do the same thing here. I should be able to bring it into one square root and have them there. You with me?
But I assume you can't because I isn't attached.
We'll talk about that here in just a bit. Let me get you there a little bit more. What's a negative times a negative? Positive. What is the square root of 81 become? 9. So it's going to come out as a 9. What does the square root of 16 become? 4. So what's my final answer? 9 times 4, because the square root of 16 became 4 on the outside, so it's 36. But the answer is actually not 36. I want you to tell me one. For bonus points, if you can tell me. The answer is actually not 36. The answer is something else. See if you can find it real quick. I will pause the video while you guys try that out.
For some reason.
Okay. Okay, so if you put this into the calculator and you get a negative 81 times a negative 16, the calculator gives us a negative 36. If you did it correctly, if you punched it in there correctly, it gives you a negative 36. Now, go ahead.
This is non-real calculation.
Okay, so it's all about that right there. The non-real calculation happens because, look guys, they're not using this property that you learned in Algebra 2 to say it's equivalent to that. The calculator knows the context that you should be looking at this depends upon something, and that's where the bonus points will come into play. Some of you saw this negative as I and the 81 as 9. Some of you saw that. And some of you saw that this becomes 4i. Because if you multiply this, this becomes 36i squared. And we remember from memorizing, this is negative 1. So it'd give me a negative 36. Now, my question to you for bonus points. Why can you not do this? Why can you not do this?
You cannot have a negative value inside the bracket.
I know that. We know that. You're right. Keep going with that, though. Why can you not use this property to get the 36 that they're getting?
Because they're not real values.
Say again?
The two negatives cancel each other.
So the two negatives.
Out the eyes.
What else?
They are not real values.
What? Just real quick. Eric? Okay, you're all on it.
I was gonna say because like division as an order.
We're dancing around it. I think we could get it, but maybe I'm not leading the question well enough. I'll say the rule that you learn. I'll just tell you the rule that you learn from Algebra 2 depends on what else you learn from Algebra 2. What is the parent function's domain? All values that are bigger than or equal to 0. So, depending on the domain, certain theorems and properties and postulates that you've learned throughout all these years will not work unless it refers to the parent function's domain. Do you understand? So this will only work for positive or real answers. The way Eric was saying, it will not work for non-real answers. Non-real answers, you actually have to do the work individually. Okay? Just a little extra FYI. Now look, let's go back to our problems here. I have 169 and I have negative 1. What does the negative 1 come out as? I. What does the 169 come out as? 13. So we have 85 plus 13i. You with me? Now, there's still some more to this I of what do they represent. I've shown you now a graph, I've shown you algebraically, and I'll even show you a different graph per se. You have these forms of A plus BI business. Okay? If I were to graph, A is relating to the X value, and B is relating to the Y value. So if I had something that said 2 plus 3i, and I asked you to graph it, what you could graph this is as a point. You could go to 2, you could go to 3, and that could be the point. You with me? If it was 2 minus 3i, you could go to positive 2, but a negative 3, and that would be the point. These are the locations based upon the quadrants. Quadrant 1, 2, 3, and then 4, based off of what their relationship between A and B and X and Y are related. Okay? So graphically, when you're graphing these pieces, that could be where the graph doesn't necessarily go all the way back to the x-axis and doesn't touch. But it could show where those are related and where they're located as far as non-real I factors. Does that make sense? Okay. So, let's do some more algebra because there's a lot of algebra with these simplifications. The square root of 16 over 49 is the same as the square root of 16 over the square root of 49. Now, I know that there's a negative there. I know there is. But am I able to use this property here like I wasn't on the other one? The answer is yes, because this one only has the one negative inside. Okay? So it's like treating it, the I comes out, that negative stays outside, and what I'm all looking at is this. So what would that simplify out to? What would the 16 come out as? 4. What does this 49 come out as? 7. So I have a negative 4/7 I. You with me? Now, if I were to graph this, negative 4/7 I, do I have an A term? No. So what is A? 0. Do I have a B term? What is it? Negative 4/7. So if I were to graph it, it would be X, Y. Otherwise, 0 and then negative 4/7. So that would be about here as a point if you were to graph it out. You with me? Yes?
What I was confused about was you can only separate the square root when there's a negative on the outside.
You can do the square root, the pieces.
Yeah.
What we were trying to do is, like Kaylee was saying, those two negatives became a positive. We were trying to put that property inside of an imaginary non-real square root. Because of the fact that those two cannot become a positive, because they're individually prime at the very beginning, they're already non-real. You see what I'm saying? This one, part of it is non-real, but not both, because it doesn't have the both negatives. Okay? With more experience, you'll understand. With more problem experience and example experience. But for now, that's what I can tell you is that you can't do the same of what we did. You can't treat it the same because there's not two non-real pieces. The product is non-real, but those pieces that can be broken up, you can do like we showed, the square root of 16 over the square root of 49. Okay? Now watch. You see this right here, and this might be incorrectly written in your notes. Please make sure you put a negative 1 on the inside. So this should say the square root of negative 5. Okay, and that becomes I, that becomes square root of 5, right? So notice the 5 stayed in. The 5 stayed in because we can't take the square root of 5, not by hand, and get an actual whole number, like an integer. Okay? And then there's just more and more practice as you go, guys. And this is the big thing that I'll say. Yeah, go ahead. The I didn't disappear because this right here should have been the square root of negative 5. So the I came out. And there it is. Okay? Now look at this. A couple other questions that I want to red flag for you guys. Okay? Combining like terms. We have negative 4i plus 5i will give us a negative 9i. We know that. This one right here is broken up, multiplicity of 2, and then FOILed out, and then common terms are grouped together. You see these 10s become 20. You see this I squared is negative 1. I squared is the main one that you're going to memorize. That's the one that you're going to use so much of. Okay? And then it's simplified. This 2 is distributed to both. From algebra 2, we knew that if it was multiplication inside, it distributes to both. So you get I squared, which is the negative 1. And this 5 squared becomes 25. So you get negative 25. Here's another FOILed example that at the very end they substituted this negative 1 where they saw I squared. So you're not really subtracting 4, you're adding 4. There's a lot of negative mistakes. And the homework is online right now. It is on the website. And it's due by midnight on Thursday with this practice, okay? A couple more I want to show you, though, before I let you go. Relate with fractions. And here we go. We see 9 plus, and you tell me, guys, what comes out from negative 144? What comes out? A 12, but not a negative 12. A 12 comes out from the 144. What comes out from this negative? I, right? So it'll be 12i all over 6. What did we learn in 5th grade? We learned how to do this. And if they had the same common denominator, if they had the same common denominator, we knew that we could write it down as one denominator with the numerators added all together on the top. And now we're just going backwards. We're going from that to this and reducing to this 3/2 plus 2i, which is what you see right here. Okay? Hold on just a bit. Reduced over here. I have too much on here right now. Let me just move it down. 3/2 plus 2i. So all it is a lot of simplifying the radicals and accounting for the fact that negative 1, the square root, is I. Now, if you are struggling with this, please keep in mind, this is something that we learned in Algebra 2. You need to catch up. I have one more slide to show you real quick. I'm going to glance over some key things that will help you for the homework, okay? Look, a little reminder. I had the following. I have a double root at 1. It balanced. I have one distinct 0. This one distinct 0 means it's different from this other one. Okay? Look at this. 3 distinct zeros means that there are 3 times that are different from one another that cross the x-axis. 1 real, there it is. And here it is. Here's the new stuff. 2 non-real zeros. Guys, this is an x cubed. It's positive, that's why it went up. The fact that it's cubed means it's going to go diagonal from one another. And do you see 3x intercepts? Yes or no? No. Because the ones that could have been x intercepts never made it up there because they're non-real. They're square roots of negatives of some sort. Okay? That's what's going on. And that's why graphically it never hit. Because we can't take the square root of negatives because the domain of square roots are 0 to infinity. No negatives. So they'll never hit the x-axis. Okay? Almost done. The last things are, we know what a double root is. It's where it bounces. Okay? And we're showing that right here. Double roots bounce off. The imaginary roots are the ones that they will not go through the x-axis. And they come in conjugate pairs. We're going to talk more about that. And then down here, whenever you look at what should be on the inside, guys, this is the last thing that I want you to make sure that you copy. So on the foldable, if you don't already have this out and already copied, please make sure that you show all of these inside pieces of what it's talking about as far as characteristics of the graph. Distinct, double roots, and now non-real roots. Here are the non-real, guys. It never crosses the x-axis. Any questions? Okay, we'll stop there. Nicely done. Go ahead and put your stuff away, please.